and I'll show you. Okay, so I'll share the solution to the quiz that you did in the previous class, and you can put the solution and compare your answers with that as well. And if there is any problem that you got it wrong, and if you do not understand it from the solution, you can let me know, and we can do it in the class. We can do those particular problems in the class as well, right? So, okay, so you can see the screen, it's visible. All right, so last time we were doing, discussing electric potential, right? And if we saw how does electrical potential vary with distances, and so that helped us develop a relation for electrical potential energy. And we did an example problem how where we saw that if we have a charged particle and it comes closer to a nucleus, an atom of nucleus, how its kinetic energy is changed into the electrical potential energy, right? Or how the two different energies are related, right? So that's what we did last time. And then we started talking about the relation between the electric field strength and the potential difference, right? Electrical potential. So we'll continue from there. And so what I was doing at this point was telling you that the electrical potential is just, you can think of electrical potential as the gradient of a graph of a potential plotted against the distance from the center. So if I have a graph that looks something like this, then suppose for a capacitor, if you have this example that I was giving for a parallel plate capacitor, this voltage and distance graph is a linear relationship. It looks something like this, right? And if I compute the gradient of this line, taking any 2 points on this line, this would be R2 V2, and this would be R1 V1, right? So the gradient would be V2 minus V1 divided by R2 minus R1, which is just change in potential divided by change in R, right? So the electric, if this thing is essentially the electric field strength, which means that if I want to compute electric field strength, it is just the gradient of a potential versus distance graph. So for example, if this was the graph, the grade computing the electric field strength is very simple. Suppose that you have a graph that looks something like this. In this case, how would you compute the electric field strength? You would take, again, your task is to find the gradient on this line. So at every point on this line, the gradient would be different, right? So what that implies is that for this graph, the electric field strength at every point would be different, right? And why is that so? Can you tell me which graph looks like this one. So for example, what I'm trying to ask you is, can you tell me what situation, or let me give you the situation. If I have a positive charge and I bring it closer to another positively charged object, what will happen? It starts to gain potential energy, right? So that's what's happening, right? If you can see over here. So I'm bringing a positively charged object to closer to another positively charged object, and it starts gaining potential energy. And that's this type of a graph. So clearly, when you're bringing one charge closer to another, suppose this is a positive charge and this is also a positive charge, and now I'm bringing one of these closer and closer and closer and closer and closer to this another positive charge, you can see that the distance between these two is changing, which is r. So so that's why the electric field strength is different at every point on this graph, because the distance r is different at every point on this graph. So is that clear? Okay, yes. Okay, good. um, you don't have Umar in class today? Okay. Okay, so this is one of the points that I was trying to get across. Now, let's do an example. Before we do an example, let me also talk about the electrical potential energy, which we talked about initially, but let's discuss it in terms of a graph, right? So electrical potential energy versus distance. Okay, so I'm going to draw a graph. Let me see if I can do it right. And so it's like this, something like this. So this is on the vertical axis, I have the electrical potential energy. Electrical potential energy, by the way, is just if I have this electrical potential in an area, it's so in some space there is some electrical potential. Then I bring any charge in that space. So, for example, there is some electrical potential in this region, right? Some V, and I bring any other charge Q. This V in this region is due to some massive charge Q, right? And I bring some other charge in this region, then there will be some energy that this charge will have, electrical potential energy, and that energy is given by the electric field strength due to this charge, capital charge Q, which would be simply Q over 4 pi epsilon naught r squared, right? This is the electric field strength due to this massive charge Q. And I'll multiply this with this small charge Q, and this gives me the electrical potential energy of this small charge Q in an electric field that was produced by this capital charge Q. So suppose if my charge, my reference discharge Q is a positive charge. I don't know why I'm having trouble speaking today. Maybe I have some throat issues, but yeah. Okay, so Now, suppose that this Q, I'm going to take two different cases, right? One would be that this Q is a positive charge, this small q, and the other would be that this is a negative charge. So for a positive charge, what happens is that the positive charge is going to come closer in this electric field produced by capital Q, which is also positive. So essentially what's happening is two positive charges are coming closer together. So when that happens, this small q, which is positive, would start gaining energy as it comes closer and closer and closer to, let me try to draw it again. I hope I can draw it properly. Yeah, so it looks something like this. So you can see clearly from this graph that as it comes closer and closer to another positive charge, means this radius r is decreasing. R is just the it is just the separation between the two charges. So if my small q comes closer to this positive capital Q, I can see that the electrical potential energy is increasing in this direction, right? And if small q is negative, then the charge would start losing energy if it comes closer and closer towards another positive charge, which is this capital Q. So it would look something like this, right? So again, you can see that it's coming closer and closer. So the distance is 0 over here, right? But it can never approach 0. And we know that you can never completely approach another charge. There will be eventually some deflection due to the electric field of the other charge. So that's why it's going to become, for this negative, it's going to go towards negative infinity, and the electrical potential energy would keep on increasing and increasing and increasing, and the electrical potential energy reaches infinity as you go towards, as you approach a charge and you become closer and closer to it, so that the separation between the two charges becomes negligible or 0. And now you can see, let me just make this a bit short. Now you can see that there is this region between these two curves, right? And you can see that these two curves, they're both approaching are at infinity. So these lines, they will keep going forward and forward. So if I extend it, it will keep going like this, and this one will also keep going like this and like this, but it will never reach but energy would never really become equal to 0, but it will become closer and closer and closer to 0. And this thing is the reason that we say that at infinity, at the distance infinity, our charges have 0 energies. Both of these charges. So this graph is for positive, when small q is positive, and this one is small q is negative. Whether it's positive or negative, we can clearly see both are approaching 0 as r becomes larger and larger and larger. So we say that when r is infinity, then the potential, then the electrical potential energy is 0, which means essentially that the potential is also 0. So this is the reason that we say that at infinity, our potential is taken to be 0. And it's not only in the case of electricity. Even when we studied gravitational potential energy, we said that gravitational potential was essentially the work done in bringing a unit mass from infinity to any point in the gravitational field. And same is the case over here. So this even in that scenario, as R became very larger, as we approached infinity, the potential energy was becoming smaller and smaller and smaller. And so the graph in the case of gravitational potential energy looked exactly like this, except one thing. Can someone tell me which is that one thing? So if I want to draw the same graph for gravitational potential energy, I'm saying that the graph would be exactly identical except one thing. Can you tell me what's that one thing that would not be here in case of a gravitational potential energy? Anyone? Think in terms of the nature of these forces, right? So in this graph, I can see that we have a charge that is positive, and I have another charge that is negative. The arrows will be the other way around. No, the arrows will not be the other way around, really. They would be in the same direction. Think like this. Think of these charges. We have positive charge and we have negative charge. The fact that we have these two different types of charges is the reason we have two different nature of forces, right? Attractive and repulsive. But what is the case for gravity? So this is for electricity. For gravity, there is only attractive force. There is no such thing as repulsive gravity, right? So gravity is only attractive. And that's because in gravity, there is no different concept of different charges or different types of, so there is no positive or negative charge. There's only a mass that's always positive, right? So mass is always greater than 0. And that's why we only have one hello, can you hear me? Am I audible? For me, it says reconnecting. Okay. All right. Okay. Perfect. Right. So the reason for me to talk about this thing was that to help you understand why taking at R equals infinity, we say that the electrical potential energy is 0, right? And it's sensible simply because of this graph that we studied. Okay, so this was one thing. Okay, by the way, I might have to leave a bit earlier today. So I guess let's do an example problem, right? And we'll finish the class at that point. So that way we'll also be done with the topic of electric fields. And in the next class, we'll start capacitance, right? Capacitors and capacitance. So, okay, so the problem is I'm going to give you a graph as well for this problem. I'm going to try to draw this graph. Suppose that I have a proton, a positively charged particle, and this positively charged particle is released from rest. So I'll try to draw it. So I'll draw it as this plus, and something was holding it, and now that it is released, so I release it, it will obviously start to move some velocity v. Now I'm going to give you a graph, right, that shows how its potential, electric potential, varies with position for this positive charged proton. So here I have R, which is in meters. Here I have potential, which is in voltage, right? So I'm not going to write a very big number. So I'll say that this is into 10 raised to power 5, right? So every number on this line is into 10 raised to power 5. So now the maximum potential is 8 into 10 raised to power 5. And then it starts to decrease. So I'm going to try to draw something like this. And then again, it increases like this. So let's see if, no, this is not a perfect curve. Try to do it again. Okay, this curve is something better. Okay, so it starts its journey from here. So that's point A. And at some point B, its potential becomes a minimum value, which is, let's say, 1 into 10 raised to power 5 volts. And then the final point is C. And at this point, its potential is about 4 into 10 raised to power 5 voltages. So the question is, first of all, compute this velocity or the speed of this positive charge particle from its journey from A to C, right? And the second part of the problem is to compute the maximum speed or the maximum speed or velocity of this positively charged particle when it's released, right? When it's released, so let's say it's released from A, when it's released from A, and then also or from C, right? So we would be finding two different maximum velocities. One when the particle released from the point A, and or the second if it was released instead from point C. All right. So how would you compute, how would you go about the first problem, velocity of the positive charge particle from its, for its entire journey, essentially from A to C? Can someone unmute and help me solve this problem? So you have to think in terms of energies, right? Because you want to compute its velocity, and you're provided with the potential at different points or at different positions of this particle, right? So what you can say is when it initially at A, you can immediately see that it has the maximum potential, which means that it has maximum potential energy. So when I release this particle from rest, that potential energy gets converted, that electrical potential energy starts to convert into the kinetic energy of this particle, which means that I can use the conservation of energy to solve the first part of the problem. And that's very simple. I'll say that all the electrical potential energy that it loses, so loss in electrical potential energy, will eventually turn into all the kinetic energy that it gains, right? Kinetic energy gained by the particle. So how do I compute this loss in electrical potential energy? It's very simple, right? Because if you remember, electrical potential energy is minus V times Q, right? Or if I want the change or loss in this electrical potential energy, then that's minus change in the potential, because the loss in potential energy comes from the change in the potential V times the value of this charge for whose energy that I want to compute. This charge Q, positive charge Q. So that charge. And this is equal to the gain in the kinetic energy. And the gain in the kinetic energy is just half mv squared. Or you can just say v squared minus u squared for gain, but u squared, u is 0 because it was released from rest. Right? So if it's released from rest, its initial velocity is 0. Now it's straightforward. You just have to compute this V. It's a positive charged proton, so you'll have the mass of the proton over here, and charge for the proton is plus E. The values here would be minus because of this common minus, and then change in potential difference. What would that be? That would be the potential at C, which was the final potential, minus the potential at A, right? So that's the change in potential, and times the charge. So I'll just put E, right? That is the electric charge for a proton, plus E, is equal to 1/2 mass of the proton times the velocity of this proton squared. So that means that the velocity of the proton squared is just 2 minus 2 times Vc minus Va E divided by the mass of the proton. And to find the velocity, I'll just square root this thing. So when I square, because when I do this Vc minus Va, I'll get a negative number, and that negative will multiply with this negative, and it would become a positive. So you can take a square root of that thing, right? Because it would eventually become positive. So this is how you will compute the velocity of this particle, right? This is the speed of this particle as it moves from A towards C. So this is the speed that it would move with. Is this clear? Any question from anyone from this part? Alicia, Anna, Hasib, Omar, clear? Okay. Okay, all right. Okay, perfect. So that's how you will compute the velocity from A to C. Now, the second part is to find out the maximum velocity of this positive charge or the proton, say when it's released from A or when it's released from C. So let's compute the second part, maximum speed when it's released from A. First, let's compute that. So we can see at A, the potential difference is 8 into 10 raised to power 5 volts, right? So that is the maximum potential difference. Now, if it's released from A, it will cover its journey to B, right? And if it's released from C, it will also cover its journey towards B, point B, right? So if I want to first find if it's released from A, then its initial potential is 8 at A and 1 at B. And if I want to find the same thing, maximum speed, when it's released from C, then its initial potential is 4 and final potential is still 1. So I have to compute the maximum speed, which means I'll again use the conservation of energy and say that all the loss in the electrical potential energy was gained in kinetic energy, right? And so again, we would have loss in electrical potential energies minus change in potential times the charge of this proton is equal to half m v squared. And now the only difference is in this change in potential difference, because this would now be minus common, and now final point is B and initial point is A. So we'll have VB minus VA times Q is equal to half mv squared. And the rest is simple. You can you can write this expression for V squared as 2 VB minus VA Q divided by the mass of this proton, right? And then you can find the velocity from here. Now, this would be the maximum speed of this proton if it was released from this point A. If it was rather instead released from point C, then everything will be the same, but the potential differences will vary. So maximum speed from C, if it was released from C. Again, you'll say that all loss in this electrical potential energy was converted into the gain in kinetic energy, and loss in electrical potential energy, which is minus change in potential difference times Q, is equal to half mv squared. This minus sign is common. Change in potential is, so it's initially released from C and it travels to B, which means that initial potential is 4 into 10 raised to power 5 volts, and final potential is 1 into 10 raised to power 5 volts. So final potential stayed same, but the initial potential has changed. So this would be minus VB, because that's the final, minus VC, which is the initial, is the times the charge is equal to half mv squared. And from here you can factor out V and find the velocity of the particle. So was that clear? Any problem? Any question? Anything that you might think that you did not get it, or you're unsure of anything? Is it clear for everyone? Clear, clear, clear. Okay. This is clear as well. No questions? Okay, clear. Omar, Hasid, Alicia, it's clear? Okay, so if there is no questions from your side, any question, anything that you'd like to answer, can you repeat again the next step?